Welcome to The Debate. Today we're immersing ourselves in one of the most radical, definitely record-shattering feats of modern vehicle engineering, the McMurtry Spéirling. And specifically, we're going to be dissecting its audacious Downforce on-demand system. This is this small, electric single-seater that uses fan power to generate ground effect. Well, regardless of vehicle speed, fundamentally challenging how we think about grip and performance. So, the central question emerging from the material here is pretty essential. Does the Spéirling's fan-assisted ground effect system represent a truly superior, maybe paradigm-shifting method for generating downforce? Or is it perhaps an overly complex and, practically limited application when you weigh it against conventional speed-dependent aerodynamics? Now, I'll be arguing the position that this system is demonstrably superior, it's transformative. Its performance capabilities just dwarf those limited by, well, the physics we thought we knew.
And I'm coming at this slightly differently. Well, look, no one's denying the sheer spectacle. The technical achievement here is undeniable. But I maintain that this revolutionary system, for all its brilliance, it's just heavily reliant on very specific, I'd even say fragile, operating conditions. I think we need to look past the sort of headline numbers and really scrutinize the enormous engineering compromises and, frankly, the continuous power requirements that prevent it from being, a universally superior design solution.
Okay, let's start with the fundamental paradigm shift then. Traditional ground effect, as we know, relies entirely on velocity. The mechanism underneath it all is Bernoulli's principle, right? The faster air moves relative to slower air, the lower the pressure becomes. So you need air rushing underneath the floor, channeled by diffusers to create that necessary low-pressure zone. This means the force is governed by the square of velocity. You simply have to be moving very fast for meaningful downforce to materialize. The Spéirling, well, it utterly bypasses the speed dependency. The twin-fan system generates 2,000 kilograms of downforce, instantly, irrespective of speed. Now, to put that in perspective for everyone, that's 2 metric tons of force, nearly 19,620 newtons, generated even while the vehicle is completely stationary. The car itself only weighs about, 1,300 kilograms? This means the Spéirling is capable of exceeding its own weight in downforce before the wheels even turn. The ability to, theoretically at least, remain attached to a ceiling.
Theoretically, yes.
A feat utterly impossible for a stationary Formula One car. That's the ultimate proof, I think, that this is a superior engineering paradigm. It unlocks cornering performance that was, previously confined to science fiction.
That's certainly a powerful presentation of the outcome, the result. But I would frame the engineering pathway quite differently. The phenomenal performance, like that track record it set beating a conventional F1 car at the Tabor circuit, which is impressive, it is achieved, I grant you, but only by, essentially brute forcing a pressure differential through tremendous, continuously applied energy. The system is entirely dependent on an external power source, 235 horsepower allocated purely to fan-powered adhesion. The engineering analysis needed to achieve that vacuum, it's truly extreme. You've got these 2 powerful fans that have to accelerate the air underneath the car to an incredible velocity. We're talking 147.65 meters per second. That's over 530 kilometers per hour.
Under the car, yeah.
Under the car, just to create the required pressure differential of 13,080 pascal. Now, to give that figure some context, 13,000 pascals, that's a pressure drop equivalent to what you might experience several feet underwater, or maybe close to 1/8 of atmospheric pressure, engineered beneath the car. This level of continuous extreme air manipulation, it just requires constant power input. And, it introduces inherent points of fragility into the system.
But I think you might be focusing too much on the cost of the power and not enough on the utility of the outcome. We're discussing an electric vehicle platform here that already delivers, well over 1,000 horsepower to the wheels. So allocating 235 horsepower to fan-driven grip, rather than just adding, say, marginal capacity for straight-line acceleration, actually delivers a disproportionately high return in overall track performance. The instantaneous, overwhelming grip completely changes your cornering strategy. Think about it from the driver's perspective. Conventional aero might give you maybe 500 kilograms of downforce at medium speed, right? But that force quickly degrades as you brake hard for a corner. The Spéirling, though, it guarantees 2,000 kilos of downward force the moment the throttle is touched, regardless of cornering speed. This allows for just unmatched low-speed cornering.
And that's the real reason behind those exceptional 0-100 kph times, under 2 seconds. Grip is always the limiting factor in performance. The Spéirling essentially removes that limit.
Okay, I'm still not entirely convinced that converting high-cost electrical energy into downforce is strategically superior to exploiting the kinetic energy that's already available. I understand the performance utility, I do, but let's be rigorous about the efficiency comparison for a moment. The system demands 235 horsepower be continuously supplied to those fan motors just for adhesion. That power has to be generated, it has to be stored, managed, and it inevitably affects battery life and, of course, heat generation. Traditional ground effect, while yes, it's speed dependent, it uses the air flowing past the vehicle, which is essentially a byproduct of momentum for downforce. Once the vehicle is moving quickly, that energy extraction is effectively, free from an energy budget perspective. When we're analyzing system superiority, we have to weigh system efficiency. The Spéirling pays an extremely high continuous energy tax, whereas conventional aerodynamics, they exploit the kinetic energy that's already an inevitable part of the vehicle just moving through the atmosphere. That free aspect of velocity-driven downforce offers a certain elegant efficiency the fans simply can't match.
But the value proposition here isn't really energy efficiency over some continuous, steady-state period. It's performance utility in the dynamic environment of a racetrack. What good is elegant, free downforce if it's not available when you need it most? Which is precisely during the braking zone and at the low-speed corner apex. Those are the moments, aren't they, that separate a fast lap from a record lap? The Spéirling guarantees those 19,620 newtons of force at zero velocity. This ability fundamentally revolutionizes corner attack and exit speeds. The driver can apply power earlier, more aggressively, because the grip is simply assured. That is efficiency, defined by maximizing performance, not necessarily minimizing power draw.
But, okay, that utility comes with an Achilles heel, one that conventional aero doesn't suffer from to nearly the same catastrophic degree: an extreme reliance on surface integrity. The entire system fundamentally relies on maintaining a near-perfect seal between the ground and the car's underside to sustain that massive vacuum. The fan system is, by necessity, it's a closed-loop pressure system. If that seal is compromised, even momentarily, the high-pressure ambient air rushes in, the pressure differential collapses instantly, and you lose 2,000 kilograms of downforce, just like that, in a fraction of a second. And this fragility wasn't just theoretical, it was evident in real-world testing. We saw that specific incident you mentioned at the Tabar circuit, where the car encountered a transition between two different surface types, a minor, pretty common imperfection you'd find on any track. The car momentarily lost that seal, the downforce collapsed dramatically, and it suffered a really alarming near spin. Now, conventional aerodynamic elements, while maybe less forceful at low speed, they're designed to handle imperfections and surface changes without the risk of sudden, catastrophic loss of adhesion. They might degrade gracefully. The Spéirling system, it seems, can fail quite abruptly.
Right. I see why you'd frame that surface dependence as a fatal flaw, but I'd argue you're maybe mistaking a challenge common to all ground effect vehicles for a fundamental design defect specific to this one. Any car designed to operate with such incredibly low ground clearance faces risks from surface changes. The key difference here is the sheer magnitude of the force being provided. The enormous vacuum created by these powerful motors, you said, each rated around 118 horsepower, running at a screaming 23,000 RPM, it provides such an overwhelming amount of grip that the momentary risk of breaking the seal becomes, I think, an acceptable trade-off for the unprecedented performance gains. I mean, furthermore, the vacuum itself is so profound it can literally vaporize standing water on the asphalt into a dense cloud ejected through the diffuser. That doesn't sound like a fragile system to me. That sounds like a system exerting massive, proven physical control over its environment. The engineers have worked on mitigating this seal risk through skirt design and management. And the occasional hiccup, well, it doesn't negate the system's overall efficacy, in my view.
Well, mitigation is certainly required precisely because the system is fighting basic physics. And the necessary ancillary compromises, I think, really underscore this struggle. I want to highlight the measures required just to achieve the sort of showpiece ability, that inversion stunt, which really demonstrate how far the engineers had to stretch the design envelope. For instance, to manage the enormous load at the 90-degree transition point during the vertical run, the engineers had to add a non-structural element, basically a sticky, abrasive patch applied specifically to the track surface, just to ensure enough friction for the wheels to continue gripping at that critical moment when the downforce transitioned to lateral force. That's a concession to physics outside the core vehicle design, isn't it? And perhaps more tellingly, consider the fundamental redesign of the cooling system. Standard vehicular cooling systems, they intentionally leave an air reservoir at the highest point to purge air bubbles and ensure the pump is always immersed in liquid. When a car is inverted, obviously the highest point becomes the lowest point, risking air ingestion into the pump, which would be a catastrophic failure in high-performance cooling. The solution wasn't some minor tweak, it was to fully fill all cooling reservoirs, leaving absolutely no airspace whatsoever. Now, these aren't minor integration issues. These are fundamental, non-trivial redesigns of basic vehicular systems required just to force the car to break the natural rules of physics. It really reveals, I think, a deep engineering struggle.
Okay, that's a compelling point, but I'd frame those redesigns not as struggles necessarily, but maybe as instances of systems integration mastery required to achieve something truly revolutionary. When you're pioneering a system capable of generating 19,620 newtons of force independent of speed, you absolutely must expect to encounter and, solve novel integration issues. The fact that the engineers did successfully integrate these highly powerful fan motors, manage the massive electrical demands, and meticulously solve these corollary issues like the cooling system's inversion requirement, that simply validates the system's robustness and its potential, in my eyes. The core value, the ability to convert conventional electrical power into overwhelming, speed-independent grip, that remains the true revolution here. The fact that they took the trouble to solve for scenarios like driving upside down only proves their commitment to maximizing the utility of speed-independent downforce. It demonstrates that the problem of generating maximal grip without velocity is in fact solvable.
Solvable, yes, I'll grant you that, but perhaps only within an operational envelope that is inherently quite brittle. If you step outside the perfect specialized track conditions, if the surface changes dramatically, or perhaps if the power demand for the fan system exceeds what the battery can continuously deliver while also powering the 1,000 horsepower drive motors, the entire premise of the design is severely jeopardized. The fan system demands constant near-perfect conditions. Conventional aerodynamics, for all their speed dependency, they are robust across far wider variances in operational environments. We're looking at a system, I think, that works brilliantly right at the extreme limit of engineering, but is intrinsically defined and maybe constrained by those very limits.
And I would contend that the annihilation of track records proves that this extreme limit is precisely where true unconstrained performance actually lies. The performance delivered justifies the complexity and, yes, the power cost.
I still disagree that it represents a viable paradigm shift for, let's say, general scalable application. But I absolutely agree it is an astonishing piece of bespoke machinery designed purely for track-specific records.
All right, so to summarize my position, the McMurtry Spéirling's fan system offers an unprecedented, really valuable alternative to classic aerodynamics. By converting conventional power into instantaneous, overwhelming grip, again, 2,000 kilograms available at zero speed, it delivers performance levels previously considered impossible. It overcomes that fundamental speed dependence
that has limited ground effect for decades, providing a continuous, controllable performance advantage right across the entire velocity curve.
And my position remains that while the power figures and the precise engineering calculations certainly confirm the system's raw capability, the reliance on continuous external power, the absolute necessity of maintaining a perfect ground seal, and that whole cascade of ancillary system modifications from cooling redesigns to needing external surface aids, they place significant practical limits on its superiority compared to the efficiency and, I'd argue, the relative robustness of traditional velocity-driven ground effect.
Well, we certainly agree that the material provides some absolutely fascinating detail into the outer limits of vehicle engineering and what is possible when design constraints are essentially removed.
Indeed. It forces us all, I think, to weigh the incomparable value of unconstrained, immediate performance against the inherent constraints of complexity and perhaps practical fragility in the engineering solutions required to achieve it.